Welcome to our second presentation for Chapter 6. In our previous presentation on the electronic structure of atoms, I taught you guys how to devise an element's electron configuration. Now you may notice that an electron configuration can be pretty long for elements that are further down the periodic table. For example, the electron configuration of bromine, element number 35, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Whew. I doubt that most of you guys want to write something that long out. I know that I don't. So what in the world can we do? Well, instead of writing the longhand electron configuration for an element, there's a shorthand or condensed way of doing it. Using this condensed approach, we just write in brackets the symbol for the noble gas that comes before the element on the periodic table. Then we write the rest of the electron configuration between that noble gas and the element in question. For example, if we wanted to, we could write out the longhand electron configuration of phosphorus as being 1s2, 2s2, 2p6, 3s2, 3p3. Or we could just notice that the noble gas that precedes phosphorus on the periodic table is neon. We could then write the shorthand electron configuration of phosphorus by describing all the electrons between neon and phosphorus. This would be done as follows. We write neon in brackets, and then we just write the electron configuration between neon and phosphorus, which is 3s2, 3p3. This is called a shorthand or condensed electron configuration. So let's do a problem. Question number 9 from problem set 6. I want you to write the condensed electron configurations for the following atoms using the appropriate noble gas core abbreviations. For problem set 6, question 9, we are asked to write a condensed electron configuration for the atoms listed. Now I'm going to not do all of those. I'll just pick one at random. I'll pick selenium, letter E. If we look at the periodic table, we can see that selenium is element number 34. So this is element 34. If I were to write the entire electron configuration for selenium, it would take me a while. However, I am going to write the abbreviated electron configuration for selenium. What I do is I realize that the noble gas that precedes selenium on the periodic table is argon, element number 18. So I write argon with brackets around it, and when we see this, that denotes the entire electron configuration for argon. Now all I do is I add electron configurations for everything in between argon and selenium. So after argon, element number 18, we go to element number 19, potassium, which is on row 4s in the S block. I count up. Potassium is in 19, calcium is in 20, 4s2. Now I move into the D block with element 21. Now you might remember me telling you that D orbitals on the same row in the periodic table are actually one energy level lower than the S orbitals and P orbitals in the same row. So in other words, on row 4, potassium and calcium correspond to 4s orbitals. But as soon as I get to element number 21, scandium, I am in the 3d level. And now I count up. Elements 21, 2, 3, 4, 5, 6, 7, 8, 9, and 30 all take me through the entire D block in that row with 10 electrons in it. I'm now at element 31. Element 31 is gallium, which is the first element in the 4p row. I now count up 31, 2, 3, and 4. I'm finally at element 34, selenium. which has 4 electrons in the 4p row. So this is the condensed or abbreviated electron configuration for selenium. Let's see if we can pick a different element. We'll pick lead. So letter C is lead. If I look at the periodic table, lead is element number 82. Once again, if I were to write the entire electron configuration for lead, it would be very long. But I don't have to. I'm going to look and find the element that precedes lead in the noble gas column. The noble gas that precedes lead on the periodic table is xenon, element number 54. So I write xenon in brackets, and now all I need to do is write the remaining electron configuration between xenon and lead. So the next element after xenon is element 55, cesium. Cesium is in row 6, so it has a 6s. If I count up cesium 55, barium 56, that corresponds to 2 electrons, so 6s2. Now one thing that can be confusing is remembering that the next element in the periodic table after barium is not element 71. It's actually element 57, which is down here in the F block, which is frequently and typically shown underneath the periodic table here, or underneath the D block in the periodic table. So these are the lanthanides. So I go 55, 56, and now I get to the F block. Well, the first element in the F block is actually a 4F. This is really kind of confusing, but if you look at the periodic table that I showed you earlier in our PowerPoint presentation, you'll see that the first row of F's actually starts at energy level 4. That indicates that F orbitals are closer to the nucleus than the S orbitals are in the same row. So I start counting up my F's. I count them all up, and I will end up seeing, as I go from element 57 all the way to 70, that I indeed have 14 electrons. Once we hit 70, we now go to element 71. Element 71 is in the D block, and it is 5D. I start counting across from element 71 all the way to 80, and I've gotten now 10 electrons. I'm now going to the next element, 81, which is in the 6p row, and I count until I get to lead, which is 2 slots in. So this is the abbreviated or condensed electron configuration for lead. I'll let you guys work on the remaining problems from that question.
Now at this stage you may be asking yourself, so now that I know how to assign an element its electron configuration, what in the world does that tell me? Rest easy, my dear student, for I'm about to tell you the answer. Do you remember me teaching you earlier in our previous presentation about quantum numbers and orbitals? Well, this stuff all goes hand in hand. You see, for every part of an element's electron configuration, this number represents the principal quantum number or energy level, n. This letter represents the shape of the orbital in question, in this case, an s orbital. And this number represents how many electrons, in this case 2, are occupying the orbital in question. So let's return to oxygen, which has an electron configuration of 1s2, 2s2, 2p4. Here's oxygen's tiny nucleus, where its neutrons and protons are kept. Around the nucleus is a spherically shaped 1s orbital. It contains 2 electrons. Outside of the 1s orbital is a larger, also spherically shaped 2s orbital, which also contains 2 electrons. Outside of the 2s orbital are 3 dumbbell-shaped 2p orbitals, oriented along the x, y, and z axes. Now you'll notice that the last part of oxygen's electron configuration, 1s2, 2s2, 2p4, says 2p4. This means that there are 4 electrons occupying oxygen's 3 2p orbitals. So where do these electrons go? Well, they fill up these orbitals one at a time. In other words, electrons won't pair up to occupy the same orbital until there's no other option left. This is called Hund's rule, although it's worded in your book in a really baffling manner. So this means that the 4 electrons occupying each 2p orbital fill up like this. The first one goes here, the second one goes here, and the third one goes here. Now keep in mind that each of these dumbbells is one 2p orbital. And there are 3 total 2p orbitals, one along the x-axis, one along the y-axis, and one along the z-axis. So thus far, I've had 3 electrons be able to each occupy an orbital and not be paired. Oxygen has a 4th electron, however, and there is not a 4th 2p orbital. It's not going to go into a higher energy orbital like a 3s orbital because that would be less stable than pairing. So where does that 4th electron go? Well, it ends up having to go in to one of the same orbitals as the other. So these 2 electrons, one here and one here, are indeed paired and are both occupying this orbital, this 2p orbital that is found straddling the x-axis. Now you should remember that the 2 paired electrons in the 2p orbital along the x-axis are different from each other because one of these has a plus 1/2 spin and the other has a minus 1/2 spin. So when we talk about oxygen having an electron configuration of 1s2, 2s2, 2p4, this is what we're talking about. We're saying that in oxygen's 1s orbital, there are 2 paired electrons. In its 2s orbital, there are 2 more paired electrons. And in its 3 2p orbitals, there are 4 electrons. 1, 2, 3, and 4. 2 of which, these 2 along this x-axis 2p orbital, are paired. And the other 2, one in the y-axis and the other on the x-axis, are unpaired. Now this cool/lame table from your book shows us an alternate way of portraying several elements' electron configurations. You'll notice that the up arrow denotes a plus 1/2 spin, and the down arrow denotes a negative 1/2 spin for electrons that are paired within the same orbital. So if we look here at lithium, for example, its electron configuration is 1s2, 2s1. This means that in its 1s spherical orbital, it has 2 paired electrons, and they go, one having a positive 1/2 spin and the other having a negative 1/2 spin. Its 1 electron occupying the 2s orbital fills in here completely unpaired. We can follow an analogous pattern as we move forward, showing these similar diagrams for these other elements on the periodic table. So let's do a problem. Question number 10 from problem set 6. I want you to identify the specific element that corresponds to each of the following electron configurations and then indicate the number of unpaired electrons that it has. Now, as I've done in the past, you guys are welcome to pause the video right now if you wish and attempt to do these problems on your own before you tune into my answers that are forthcoming. I should warn you, as I have in the past, that I won't give you the answer to every single question, but just a few of them to get you started and allow you to do the rest on your own.
We'll now take a look at problem set number 6, question 10, which asks us to identify the specific element that corresponds to each of the following electron configurations that indicate the number of unpaired electrons that it has. Let's begin with letter B. So letter B, we're given the electron configuration 1s2, 2s2, and 2p4. As we look at the periodic table and try and figure out where that is, we'll notice that 1s2 takes us from hydrogen to helium, and then 2s2 goes through lithium and beryllium, and 2p4 takes us 4 elements in to element number 8, which is oxygen. A really easy way to do this is to remember that these superscripts represent electrons. So if I add those up, 2 plus 2 plus 4 equals 8, that is the number corresponding to the element on the periodic table. So this is atomic number 8, which is the atomic number of oxygen. So that answers the first part of the question. The next part of the question is asking how many unpaired electrons does it have? Well, you should remember that these electrons fill up their orbitals from the innermost orbital to the outermost orbitals in order. So this 1s orbital, which is a sphere, has 2 electrons in it, which are both paired. There's a 2s orbital, which is larger and also spherical outside of the 1s orbital, and these 2 electrons are also paired inside that orbital. 2p orbitals represent 3 dumbbell-shaped orbitals on the x, y, and z axes like this, and I have 4 of them. Those electrons will go into each orbital unpaired until they have to pair. 1 electron goes into one orbital, second electron goes into a second orbital, a third electron goes into the third orbital, and the 4th electron is required to go into that same third orbital because there's not a 4th p orbital to go into. So the question asks us, how many unpaired electrons are there? Well, there's 1 unpaired electron here and here. So the answer is 2 unpaired electrons. Now we'll do problem set 6, question number 10, part B. I'm not sure why I picked that one, just because I thought it would be fun. So the electron configuration that we're given is krypton, 5s2, 4d10, 5p4. What element does that correspond to? Well, I'm going to look at the periodic table, find krypton, and then continue on down the line. 5s2 takes me from rubidium to strontium. 4d10 takes me all the way across that row of Ds. 5p4 takes me 1, 2, 3, 4 elements into element number 52. So that takes me to element 52 from the periodic table, which is tellurium. So that answers the first portion of that question. The second portion of the question is to figure out how many unpaired electrons are there. One way you can do this, once again, is to just look at the orbitals. A 5s orbital is going to be spherical in shape. It's going to be much larger than the lower s orbitals, of course. It contains 2 electrons, which are both paired. The 4d block has 10 electrons in it, and that is an even number, and all of those are going to be paired. 2 electrons in each of the 5 4d orbitals. Now we'll get to the 5p orbitals, and I'm going to kind of refrain from drawing the 4d orbitals just because they're really a little bit crazy. The 5p orbitals are, of course, going to be dumbbell in shape, 1 along each of the axes, z, y, and x. I've got 4 electrons, and they fill up unpaired, 1, 2, 3, until we get to the point where we have to pair 1. So the other electron is going to pair into this orbital. These 2 electrons are paired. These electrons right here are unpaired. So the answer is 2.
We'll now go back to oxygen, remembering that its electron configuration is 1s2, 2s2, 2p4. You might recall from our earlier slide that the 2 electrons in the 1s orbital are buried deep beneath the 2s and 3 2p orbitals, like this. The 2 1s electrons are called core electrons because they're buried too deeply to easily reach. The 6 combined total electrons in the 2s and 3 2p orbitals are called valence electrons. These are the electrons that actually participate in chemical reactions. So oxygen has 6 valence electrons, 2 in its 2s orbital and 4 in its 3 2p orbitals. It wants to gain 2 more to obtain a noble gas configuration like that of neon. Now you should note that oxygen's valence electrons are further away from its nucleus than its core electrons. This means that its valence electrons are more reactive, less stable, and higher in energy than its core electrons. In fact, for all electron configurations, the higher the principal quantum number n, the further away from the nucleus, less stable and more reactive the electrons are. This is shown in the figure to the right, which we call an energy diagram. So you can see this energy diagram portrays the most stable electrons, which are in the 1s orbital closest to the nucleus, as being down here. We go higher energy, less stable, more reactive in the 2s and 2p electrons, shown up here. We can see then that any group of orbitals that have the same n number, such as 2s and 2p, also have the same energy level. This then would be the way of drawing oxygen's electron configuration, 1s2, 2s2, 2p4, in an energy diagram. Remember that we fill up each box from the bottom, lowest energy, down here, to the top, highest energy, in order. Electrons don't like to be paired up unless it's necessary in order to avoid going to a higher energy level. So we don't pair up electrons in the same energy level until we have to. So let's see if we can fill these up for oxygen. Oxygen has 2 electrons in its 1s orbital, so I fill them up. One has a plus 1/2 spin, one has a minus 1/2 spin. Now oxygen's next electrons are in its 2s orbital. It's going to have one as a plus 1/2 spin and one as a minus 1/2 spin. Now it has 4 electrons in its 2p orbital, and they're going to first occupy the 2p orbital completely unpaired. So 1, 2, 3. Now the 4th electron now has a choice. It could either go in the 3s orbital up here, or it could pair up and stay in the 2p. It's much more stable to stay paired up, even though electrons don't like to be paired up because they tend to repel each other. Thus the 4th electron does pair up and ends up here in this 2p orbital shown here. This electron configuration, 1s2, 2s2, 2p4, represents oxygen's most stable configuration, which is called its ground state. Now, electrons can be promoted to higher energy levels, usually by pumping energy into the system. For example, if we pass electricity through an oxygen atom, the influx of energy can cause one of its valence electrons to jump up to a 3s orbital like this. You can see how the electron went from its 2p orbital up to the 3s orbital. I hope, at least. Let's take a look at it again. We'll go back. So here is oxygen's ground state. We have all of these electrons in the 2p orbital, but if I pump some energy into oxygen, one of those electrons will go unpaired up to the 3s orbital. Let's go back and forth and watch it happen. Woo. Woo. Oh yeah, that's exciting. Okay. So this circumstance where one of the electrons has been promoted to a higher energy level is called an excited state. Even though the 3 electrons in the 2p orbitals are now all unpaired, it's still less energetically favorable, less stable to have one electron up here in this higher energy 3s level. Hence, the promoted electron up here in the 3s orbital will eventually fall back down to the 2p orbital. And when it does, it will give off energy, usually in the form of heat or light. Now this is how a light bulb works. For example, a neon light functions because electricity, energy, is passed through a bulb that is filled with neon gas. The neon gas's individual atoms, valence electrons, then get excited and get promoted to a higher energy level called an excited state. And then as those electrons fall back down to their ground states, they give off colorful light. This, just so you know, is our fun fact for the day. I'll now return to this figure and do some explaining that I promised I'd do during our last presentation. Do you guys remember how I said that the D block over here starts at 3D, even though it begins on row 4? Also, I told you guys that the F block starts at 4F, even though it begins on row 6. Now, the reason for this is because the very first d orbitals here are actually closer to the nucleus and lower in energy than the s and p orbitals that are found in the same row. That's the reason why the first row of d orbitals are actually at an energy 3 level, one level more stable than the s and p orbitals in the same row. An analogous thing occurs for the F block elements here. This might seem super weird, but it's totally true. We'll now finish with one final problem, question number 11 from problem set 6. I want you guys to figure out what is wrong with the following electron configurations for atoms in their ground states. As I've done before, I will be sharing the answers with you, but you're welcome to pause it first and try these on your own before you have me go ahead and dictate the answers to you. As I've done in the past as well, I won't show you all the answers, but just a few, with the hope of getting you started and letting you do the rest on your own.
We'll now examine problem set 6, question number 11. What is wrong with the electron configurations for atoms in their ground states? So question A says 1s2, 2s2, 3s1. If we look at the periodic table and try and reason our way through this, we can see that 1s2 tells us a nice ground state of 2 electrons occupying the first 2 elements in the p block. 2s2 looks great, but then we have one electron that totally skipped the 2p row and went all the way up to a 3s row. So when it asks us the question, what is wrong with the following electron configurations for their ground states, you would say, this electron should be in the 2p, or I should say in a 2p orbital in its ground state. So this is obviously not an element in its ground state. This is an element in which one of its 2p electrons has been excited all the way up to a 3s orbital. For the fun of it, we'll now do question C. It gives me the electron configuration of neon, 3s2, 3d5. Neon, if we look at the periodic table, is element number 10. As we go after neon, we hit elements 11 and 12 in the 3s orbital block. That looks just fine, 2 electrons filling that. Now, if we were to continue left to right, the next orbital that we would be hitting would be the 3p orbitals. However, the next electrons that we see are all up all the way in the 3d orbitals, which don't begin until you hit element number 21. So what this means is, in its ground state, these electrons should be in the 3p orbitals. And that answers that question.
So this seems to me to be like a wonderful place for us to stop, and it concludes our discussion and delving into chapter 6. I hope you guys all enjoy doing your problem sets. Work hard. Study the material deeply. Spend good time studying and preparing yourselves for our future exam. And I look forward to seeing you guys soon.